Hello, college algebra student. This video is for chapter 6.4, graph logarithmic functions. So basically, we want to see how a log functions behave in a graph. We learn how to evaluate them by using exponential function. And an important notes to know from 6.3 when we study log function is it is actually the inverse of exponential function. So borrowing the properties of inverse between two functions, we know if it is the domain of one function is the range of the other function. So in this case, the domain of the log function is actually the range of exponential function. So do you still remember for exponential function, they're either this case for growth and this case for decline, and both of them has a range where y is greater than 0, right? There's nothing in the negative side. Now this is the range of any basic parent exponential function b to the x. All of them has this range of y greater than 0. So the range of an exponential function become the domain of a log function. So we have this fact that domain of any log function, just the simple log base bx function would be x is greater than 0 because they are inverse of each other. So it implies that the inside of a log can never be negative. It can actually never be 0. It has to be a positive number. So anytime you write log bx as a function, x inside this log is greater than 0. We can actually kind of investigate this by using a calculator. So if I open up decimal, try to evaluate some log function value like what we did last time. Let's say log 5 is okay as a value is 0.69, but if I do negative 9, it would say undefined and negative 5. And if I say log negative even 0.001, it's still undefined. So anytime you have a negative value, it's not going to work. But if you get a very small number, it works, right? Very small number, it still works. It's just going to be a negative log value. So the lesson learned is, and it is really because the original exponential function has a range of y greater than 0. So this is a fact that we should know. Anytime you write some log value, inside of it has to be a positive number. And that is the domain of that particular log function. So in general, if I don't have those basic log function, I have a log of an expression of x like this. It is sometimes in the book they call it the argument. Then we can say to find the domain of a general log function, we just look inside the log expression, inside of the log input. That particular expression has to be greater than 0. So you basically would be solving an inequality of expression of x is greater than 0. Just recognize that anytime you write something inside here, log of something, this something has to be positive, have to be positive. So to find a domain of a log function, if someone write a log function, you would look at to find a domain. What you can do is look at the inside, write this expression of x inside log to be greater than 0, solve it, write in an interval notation, and then you can actually immediately find the vertical asymptotes. Because what happened is in a exponential function, you always have horizontal asymptote, right, of y equal to 0. And then in for the log function, which is an inverse of it, the horizontal asymptote becomes the vertical asymptote. And actually that is the boundary, right? The boundary of the domain. So it's the leftmost or rightmost values in the interval. Well, actually, I would not say it is in the interval, outside of the interval, just outside the interval. Okay. So, for example, if you say, "Oh, my domain for the log function is x greater than 0," then the vertical asymptote would be x equal to 0. Okay? Because when it is all gray, like if I say these are the place where you can have log, then the boundary is here. X is equal to 0 is the vertical line, is the VA. Okay, so let's see. Let's do some general one where the inside is not X, so the vertical asymptote needs to be found. We need to find the domain and also state the vertical asymptote. So we say to find domain of a log function, we have to write 2x plus 1, anything that is inside, okay, not outside, greater than 0. So 2x is greater than -1, x is greater than -1/2, right? You divide by 2 on both sides. X is greater than 1/2 means in interval notation that is from -1/2 all the way to infinity. What is the leftmost number? It's just at the boundary, boundary is x equal to -1/2 is the VA. It's the vertical asymptote. That is like kind of the boundary is approaching to -1/2 but never touch -1/2. What about this one, 5 minus x? So you would say, well, I don't care the base, so long as the inside has to be positive. So I solve why 5 minus x is greater than 0 for domain, okay? Because my goal is to find the domain. So this is the domain. So so I would plus x, maybe, greater 5 is greater than x. That means x is less than 5, right? Switch it over so we know what value it is. X is less than 5, that means it would be from -infinity to 5 is the domain, right? Because less than 5, if you look at the number line, it will be 5 here, all this number. So it starts from -infinity to 5 is the interval notation. So what about the vertical asymptote? What's the boundary? The boundary will be at x is equal to 5 in the rightmost boundary of the interval. So that's how you know the vertical asymptotes and also the domain. It would help us to graph a general logarithmic function. So before we graph general logarithmic function, we'll graph the basic parent function, which is just log base x, y equal to log b x. So because it's the inverse of exponential function, we also use the properties of inverse, which is if xy is in the exponential function, yx, like the points, x go to y for exponential, y go to x for log function, right? So we'll have a point of y comma x. So what we can do is whenever we want to graph a log function, basic log function, we would write the inverse first. We would say, well, this inverse is y equal to 2 to the x. Because same base, right? Same base, 2 to the x. Then we build a table for 2 to the x. 2 to the x table. So remember how to build it? -2, -1, 0, 1, 2, right? X and y. And then still remember 0, 1, because this 2 to the 1, 2 to the 1 is 2, 2 to the 0 is 1, 2 to the 2 is 4, and this is 1/2, 1/4. Remember in the last section, or actually in 6.2, I think that's how we graph it, right? But then our log base 2x would use this, but switch the x and y. We'll still call it xy, but the number is switched. So I would have 1/4 to be -2, 1/2 as x, but y is -1, and then 1, 0, 2, 1, and then 4, 2. So if you graph it, so of course you're just going to graph this one, right? So this would be, all your x would be positive. Do you see? You would have 1, 2, 3, 4, 2, 3, 4, but you have some number on here that is very close to 0, but never exceeding this, because we know that the domain, even before we graph it, we know that the domain is positive, and also the vertical asymptote is x equal to 0, right? And then the domain is on this side. So you can see that when your points are built where you have 1/4, 1/2, when it is 1/4, it shoot down to -2. 1/2 is shoot down to -1. But when it is 0, when it is 1, then it is 0. Okay, it's 1 0, not 0 1. 1 0. And when it is 2, it go to 1. And when it is 4, it go to 2. So it increase really slowly. Increase really slowly like that. Okay, it then never drop back, but it is a more increase. So try another one. What about if the base is just log base 1/4 x? So we write inverse first. Inverse, of course, is y equal to 1/4 of x, right? The same base. Then we build the two tables. The first table is for the exponent, y equal to 1/4 of x. Still remember how to build this? It's still -2, -1, 0, 1, 2, just what you did in 6.2. 0 is 1, 1 is 1/4, and this is 1 over 16. But for -1 is 4 and 16, the reciprocal. Now we're going to build a table for log y equal to log 1/4 of base 1/4 of x. So our x and y would look just the switch x and y of the original exponent because they're inverse. So I'll copy this y into x. 16, 4, 1, 1/4, 1/16. You see they're all positive number, right? And then the x would be -2. Well, the x become y, -2, -1, 0, 1, 2. So for the range, they have x and y. So I'm going to graph it. More space over here. I know the VA is here because inside the log it has to be positive, and this is how you do it. So you would write 1/6 is it's 2. 1/6 is 2. 1/6 is 2. So then for 1/4 is 1, and then for 16 is negative. Okay, so 1 is 0, but for 16, okay, and I go back like this. For 16, it is -2. And from 4, it is -1. So it is kind of like this. It go down slowly, but it shoot up close to 0. Okay. What about the last one, ln x? What is the inverse? The inverse is, what's the base, is it? The inverse is y equal to e to the x, right? To graph e to the x, did I graph it? I don't know. E to the x. We still graph 0, 1, 2, -1, -2. So if you do e to the 0 is 1. E to the 1 is 2.7 because that's what it is. E to the square, I think is e square is what? I think 7 point something. So e square, yeah, 7.4. And then we have 1 over e, which is e to the -1, right? It's 0.4. 1 over is 0.1, roughly, right? So then you would say, I'm going to use this to graph ln x. So this is y equal to e to the x. Use this table. Y equal to ln x would use the other table where I switch x and y. I would say xy, but I would have 0.1, 0.4, very close to 0, right? And then 0, and then 1, and 2. So, but this would be -2, -1, 0, 1, 2. So when I graph it, it look like something like 0.1 is -2, 0.2 is -1. Oh, I copy wrong. This is 1, 1, 1, 1, and 1, 2.7. Yes, 2.7 and 7.4. So 0 is 1. No, 1 is 0. 2.7 is 1. 7.4, very far away is this. is how you graph it.